In this video, we will look at a few questions from our worksheet on thermal conduction. Now, we'll begin with question 1. Now, question 1 says, a ship's porthole is 14 millimeters thick and has a diameter of 300 millimeters. It is made of a glass having a thermal conductivity of 1.2 watts per meter per Kelvin. If the temperatures of the inner and outer surfaces of the glass are 18 degrees Celsius and 8 degrees Celsius respectively, calculate the rate at which heat energy is lost through the porthole. So, as customary, we'll try to represent the situation, little diagram. We write down information that we have and we'll proceed to writing down the equation that we will use to calculate the desired quantity, which in this case is, of course, is the rate at which heat is actually lost through the porthole. So we're given the diameter, which of course suggests it is circular. So we'll try to represent the situation in the diagram as mentioned before, right? So we basically have more or less a circular porthole of a certain thickness. Let's try to represent the thickness. So, alright, so it is a circular porthole of diameter 300 millimeters. Now the diameter is 300 millimeters, which of course means that the radius would be a half of that, which is 150 millimeters. So the radius is 150 millimeters, and of course we will convert that to SI units when it comes to doing our calculation. Right? Now the thickness, we'll basically call that delta x. So the thickness delta x is given as 14 millimeters. Right? So the glass is 14 millimeters thick and it is of diameter 300 millimeters or radius 150 millimeters. Now, in addition to that, we're given that the thermal conductivity for this particular type of glass, so the thermal conductivity for this particular type of glass is 1.2 watts per meter per Kelvin. And we're given that the inner and the outer temperatures of the surfaces of the glass are 18 degrees Celsius. So if you like, this side with the inner temperature, 18 degrees Celsius, and the outer surface will have a temperature of 8 degrees Celsius. Right? And what we're asked to find is the rate at which heat energy is lost through the porthole. Right? Now, basically, assuming steady state conditions and that the rate of heat flow through the porthole is uniform, then the rate of heat flow through the porthole can be given by the equation Q over T is equal to K times A delta T over delta X. Alright? So this basically gives us the equation for the rate of heat flow through the material of cross-sectional area A, thickness delta X, where there's a temperature difference delta T between the two surfaces. Right? Now this equation is commonly referred to as Fourier's law. So basically, having written down our equation, we'll then basically go ahead and we'll substitute our information into our equation and we'll calculate the rate of heat flow through the particular material. Right? So substituting the values, we have thermal conductivity, which is 1.2. Now we're given the diameter from which we calculated the radius, and of course the radius is given as 150 millimeters, and of course we'll convert that to meters and we'll put it into our formula in order to calculate our area. Now, given the radius r, the area is of course given by pi r squared. So taking pi as 3.142, then this becomes 3.142 pi times r squared, which of course will be 0.15 meters. So 0.15 squared, and our delta T would of course be the difference between the inner and the outer temperatures. So 18 minus 8, that gives us 10. And that of course is going to be divided by the thickness delta X, or in some cases you may just see X for the thickness, which in this particular case is 14 millimeters, which of course will convert to meters, and this gives us 0.14 meters. Right? So that basically gives us a formula for calculating the rate of heat flow through this particular material, and we'll now basically go ahead and we'll do our calculation. All right, so we have 1.2 times 3.142 times 0.15 squared times 10. We divide that by 0.014. And this gives us approximately 60.6 joules per second, or 60.6 watts. So this is approximately equal to 60.6 watts. So bear in mind that we're calculating the rate at which heat energy is flowing through a material. And of course, the rate at which heat energy is flowing is as a unit of energy, which is a joule, divided by time, which of course is a second. So it gives us the joule per second, which of course we know to be equivalent to the watt. So therefore, the rate at which heat is flowing through this particular porthole is given as 60.6 watts, or if you want to round it up to say two significant figures, approximately 61 watts. And that was question 1 from our worksheet. Now we look at question 2 from our worksheet. Now, question 2 says, the walls of a picnic cool box consist of a 1 mm thick plastic inner and outer casing separated by polystyrene insulation of thickness 15 mm. If the box has a total surface area of 1.4 meters squared and there is a 15 degrees Celsius temperature difference between the internal and external surfaces, calculate the rate at which heat energy flows into the box. And we're given the thermal conductivities of plastic and polystyrene as 0.04 watt per meter per Kelvin and 0.006 watts per meter per Kelvin respectively. All right, so once again, we'll approach a question by first trying to represent the situation on a little diagram, and then of course we proceed to doing our calculation. So what we're told is that what we have is a picnic cool box. It basically consists of a 1 mm thick plastic inner layer and also a 1 mm thick outer plastic outer layer, between which there is a 15 mm thick layer of polystyrene, the purpose of which is to provide insulation to minimize heat loss from, or to minimize heat loss flowing into, or heat loss into the cool box. So our diagram basically will look something like this. Right, so what we have here we have our just a cross section of our cool box. So as I said before, this cool box consists of 2 layers of plastic 1 mm thick. So these layers are plastic, so this will be 1 mm, and this also will be 1 mm. And between those 2 layers of plastic, there's a layer of polystyrene of thickness 15 mm. Right, so this of course is plastic, and this would be polystyrene, and this of course would be plastic as well. So in terms of information that we're given, we're told that the total surface area is 1.4 meters squared. So the total surface area, let's call that A, 1.4 meters squared, right? Now we're told that there is a 15 degrees Celsius temperature difference between the inner and outer surfaces. So if we treat this as the inner surface and this as the outer surface, the temperature difference delta T is equal to 15 degrees Celsius. Now we're not given the inner temperature or the outer temperature. What we're simply given is the temperature difference. So for instance, this could be 20 degrees Celsius, that could be 5 degrees Celsius, this could be 40 degrees Celsius, this could be 25, and so on. So we don't know the inner and outer temperatures, but what we do know is the temperature difference between the inner and the outer layers, right? We're also given that the thermal conductivity for plastic, so I'll use that with a subscript PL for plastic. The thermal conductivity for plastic is given as 0.04 watts per meter per Kelvin. And the thermal conductivity for polystyrene, I'll write it as KPO is equal to 0.006 watts per meter per Kelvin. Right? And what we're really asked to find is the rate of heat flow, or the rate at which heat energy flows into the box. Now, for this type of question, our approach will be that of one of thermal conductors connected basically in series. Now, we would have looked at electricity in some detail before, and we would have spoken about, for instance, electrical conduction, and we would have also looked at electrical resistance. Now, when it comes to heat flow is basically more or less analogous to electricity or to electric flow, right? To current flow. And so basically what we can do is to find an expression for the thermal resistance of each layer, and because we're treating them as conductors in series, it basically means that their resistances will add similar to electrical resistances of conductors connected in series, right? So what we will do is we'll find the thermal resistance rather of each layer. We'll find the total thermal resistance, and that will basically allow us to find the rate of heat flow through the composite material. Now, the expression or the formula for calculating thermal resistance is given as RT is equal to delta X over K times E. So therefore, the thermal resistance of a piece of material of thickness delta X and thermal conductivity K and cross-sectional area A is given by this particular formula here. So what we'll do is, since the plastic, each layer of plastic is of identical dimensions and naturally it's the same material, so it will have the same thermal conductivity. We'll do that calculation once. We'll calculate the thermal conductivity for polystyrene, and then of course we'll find the total thermal, not thermal conductivity, but thermal resistance. Then we'll find the total thermal resistance of the composite material. So for plastic, we say that the thermal resistance, RT, is equal to the thickness of plastic, which is 1 millimeter, which of course will convert to meters. So this is equal to 0.001 meter divided by thermal conductivity of plastic, which is 0.04, times the total surface area of 1.4. Right? And this will give us approximately 0.01786. So 0.01786, and the units of course are Kelvin per watt. So the units of thermal conductivity is the Kelvin per watt. So having done that for the plastic, we'll also do it for the polystyrene, right? So this is thermal resistance of the plastic. Now for the polystyrene, same formula applies. So RT is equal to delta X thickness divided by the thermal conductivity K times the area A. And so the thermal resistance of the layer of polystyrene now will be given as, the thickness of course in this case is 15 millimeters or 0.015 meters. So 0.015 divided by its thermal conductivity, which is 0.006, times the total surface area, which is of course 1.4 meters squared. Right? And this will give us a thermal resistance of approximately 1.786. This is equal to 1.786, and this would be Kelvin per watt. Right? Now, what we've done so far is to calculate the thermal resistance for this particular thickness of plastic and for this particular thickness of polystyrene. But as we mentioned before, essentially what we have is a composite material consisting of a layer of plastic, an inner layer of plastic, an outer layer of plastic, between which you have a 50 millimeter thick layer of polystyrene. So basically what this basically does, it is to create a composite material of which we'll basically find the effective thermal resistance, and we treat these as resistors or thermal conductors connected in series, and therefore their resistances will add. So what we'll do now is to find the total thermal resistance for this composite material. So the total composite, the total thermal resistance, so this would be equal to the thermal resistance of this layer of plastic plus the thermal resistance of this layer of polystyrene plus the thermal resistance of this layer of plastic. But of course, since the layers of plastic are identical, we'll simply just multiply the thermal resistance of one layer by 2 and then add it to that. So this gives us 2 times 0.01786 plus 1.786. And so this gives us approximately 1.82 Kelvin per watt. So that is the total thermal resistance of this conductive material, or this this composite thermal conductor, right? Now basically similar to how electrical resistance is a measure of the opposition to the flow of an electric current, we can say that thermal resistance similarly is a measure of the opposition to the flow of what we consider to be thermal current, right? So the greater the thermal resistance, this basically means that the lower the rate at which heat will flow into or out of the particular material, right? So similar to electrical resistance, where the greater the electrical resistance is, the smaller the smaller the electric current that will actually flow along a particular path. The greater the thermal resistance of a particular composite material or a single material, then it means that the lower the rate of heat flow through the particular material, right? Now, having found the thermal resistance of the composite material, we can then now go ahead and find the rate of heat flow through the material by using the formula Q over T. So the rate of heat flow, Q over T, is equal to the change in temperature, or the temperature difference delta T, divided by the total thermal resistance RT, right? And as before, if you recall, the change in temperature delta T was given as 15 degrees Celsius, but of course when it comes to converting temperature, a change in temperature of 15 degrees Celsius will of course be the same as a change in temperature of 15 Kelvin, right? So to make sure units coincide, we treat it as being in Kelvin. So this basically gives us 15 divided by 1.82, and that will be approximately 8.2 watts, right? So therefore the rate at which heat is actually flowing through this composite material is 8.2 joules per second, or 8.2 watts. Alright, so this brings us to question 3 from our worksheet on thermal conduction. Now the question says, the diagrams show the dimensions of a solid brick wall, 2 brick thick, and a cavity wall with polystyrene insulation. In each case, the interior and exterior surface temperatures are 18 degrees Celsius and 4 degrees Celsius respectively. calculate the heat energy conducted per second through 5 meters squared of each type of wall. So we're given diagrams to represent the situation. Of course, we show the diagrams, and we're also given the thermal conductivity of brick, and we're also given the thermal conductivity of polystyrene, which basically forms the insulating layer between the composite wall, which is insulated, right? So the solid wall basically looks something like this. And we have 2 layers of brick which are equal in thickness. Try to make this look even as possible. Right, so each layer is of thickness 120 millimeters, 120 millimeters. So the composite thickness of the wall would be 240 millimeters, right? So we're talking about 2 layers of brick. The inner layer is at a temperature of 18 degrees Celsius, and the outer layer is at a temperature of 4 degrees Celsius. So of course both of these are layers of brick, right? We're given that the thermal conductivity of brick, I'll call it KB, is 0.50 watts per meter per Kelvin. And we want to find the rate at which heat is conducted through the wall for an area of 5 meters squared. So the area we're dealing with, A, is equal to 5 meters squared, right? Now we could take a couple different approaches to this particular question, and of course we will actually look at different approaches to the question where we'll make some assumptions for each approach, and at the end we'll be able to determine if our assumptions were indeed correct, right? So we'll begin by looking at this particular situation. Right, so what we have here is a 2 brick thick layer wall, 2 brick thick wall. Inner temperature is at 18 degrees Celsius, outer temperature is at 14 degrees Celsius. We have the thermal conductivity of brick, and we're also given the area of the wall in consideration, right? So we could make some assumptions that the rate of heat flow through each layer of wall is basically uniform, and we could also basically assume that the temperature gradient along each layer of wall is also uniform, which basically means that the temperature gradient through the composite layer is uniform as well. And if we make those assumptions, then we can basically write down our formula for calculating the rate of heat flow and substitute our values directly into our formula to calculate the rate of heat flow. So let's do that. So we can say that assuming steady state conditions, meaning that basically the temperature at each point along the wall is more or less constant, then the rate of heat flow is given by Q over T is equal to K times A delta T divided by delta X. Again, sometimes we may just put X for the thickness, but if you see X or delta X, that basically means the same thing. So in this particular case, we're talking about a 2 brick thick layer of wall, and so of course it's the same material, so the thermal conductivity will be uniform throughout. So this of course gives us 0.5. We're given that the area of the wall in consideration is 5 meters squared, so this would be 5. Delta T would be the difference in temperature, of course, between the inner and the outer layer. So 18 minus 4, that will give us actually 14. And we'll be divided by the thickness of this composite wall, which in this case is 120 plus 120, 240 millimeters, which of course must be converted to meters. So this gives us 0.24 meters. And we simply go to our calculator and we work this out, right? So we get 0.5 times 5 times 14 equal, divided by 0.24, and that gives us approximately 145.8, or if we want to round it up, we could say 146 watts. So this is approximately equal to 146 watts, right? So that was the first approach of doing this particular question. Now, as I mentioned before, we will take a second approach. Now, this second approach will involve finding the temperature at this layer where at that junction, where the two layers of brick would meet, right? We could approach this question in different ways, right? So let's do that and see if it actually works out to agree with our assumptions. So we basically say that assuming steady state conditions, the rate of heat flow is uniform, right? So assuming steady state conditions, the rate of heat flow is uniform, which basically means that if we call this bricklayer 1 and bricklayer 2, then this would mean that the rate of heat flow through layer 1 is equal to the rate of heat flow through layer 2, right? And of course, the rate of heat flow is given by this equation here. So we can just go ahead and substitute our information. So it's the same brick, so the K will remain the same. So we have K, that's right, the same area A. Now in terms of the temperature difference, delta T, in this case, the temperature difference would be, for layer 1, temperature difference would be 18 minus T. So this is Ka times 18 minus T, and the thickness of course would be 120 millimeters or 0.12 meters, right? And this would basically be Ka. In the case of the second layer, the temperature difference delta T would be T minus 4. So this would be T minus 4 over the same thickness, 0.12. Now essentially now we have the same thing on some either side of the equation, like for instance, the 0.12s can cancel each other, the K's can cancel each other, the A's can also cancel each other, and so what we're left with is 18 minus T is equal to T minus 4. If we bring all the T's to one side, we can then solve for T, and we can basically find the value of the temperature at this junction where the two layers of brick would actually meet. So bringing all the T's to one side, we get 18 plus 4 is equal to 2T. 2T is equal to 22, and so therefore T would be equal to 11 degrees Celsius, right? So if T is equal to 11, then we can actually then now use the information for either bricklayer 1 or bricklayer 2 to actually find the value for the rate of heat flow through the composite wall. And so using the information for bricklayer 1, we can then say Q over T is equal to Ka delta T divided by delta X. And so this gives us Q over T equal thermal conductivity, which is 0.5, area, which is 5. Delta T in this particular case now would be, so this here, T would be 11. So since T is equal to 11, for bricklayer 1, this delta T will be 18 minus 11, which gives us 7. So delta T is 7. And the thickness delta X will of course be equal to 120 millimeters or 0.12 meters, right? And so if we look at that, we see that approximately the difference between that value over there and this is that instead of 14, we have 7. So that's a half of that. And we also have the thickness we're dividing by. So basically, this works out to be the same thing. So the rate of heat flow is approximately equal to 146 watts. So basically what this shows is that it agrees with our initial assumption that the rate of heat flow through the entire composite wall is basically uniform. And so basically what we did was to just use the inner and the outer temperatures and to find the rate of heat flow through the 2-layer thick brick wall, because of course the material was indeed the same type, right? Now bear in mind that if this was 2 different types of material, then we could not have done that. We'd have actually basically had to find for instance the thermal resistance of each layer of material and then basically find the rate of heat flow by using the formula we'd have used before, right? So we tried 2 different approaches for this particular question, And of course, the results show that both approaches would have been correct. Now, that was actually part A of the question, where the composite wall basically comprised 2 layers of brick with no insulation. And now we'll actually do the question where there is insulation between the layers of brick, and we shall actually see the difference in the actual rate at which heat is actually flowing through the wall. And then we may start to appreciate the importance of insulating materials. So I'll leave that on the board there for comparison purposes. Right, so in this part of the question, what we have is another brick wall, but this time in between the 2 layers of brick is going to be a layer of polystyrene. So that be the brick, that be the brick. This of course is polystyrene, right? So brick, brick, polystyrene, right? So once again, the thicknesses are the same. Other brick, that is 120 millimeters. Thickness of the polystyrene is given as 60 millimeters. Temperatures, same as before, 18 degrees Celsius, 4 degrees Celsius. Now, in this particular case, the situation is different. It's not the same type of material which forms the different layers. On the outer layers, of course, you have the same material, brick, but on the inner layer, we have polystyrene, and therefore we can't take the approach that we would have taken before. However, what we will do is to basically treat this as a composite thermal conductor, or as 3 thermal conductors in series. We will find the thermal resistance for each layer, and we'll then find the total thermal resistance, and then of course we'll be able to find the rate of heat flow by using the thermal resistance, right? So the thermal resistance, RT, is given by delta X over K A. And of course, we'd have been given the thermal conductivity of brick and polystyrene as well. So let's deal with the thermal conductivity for the brick. For the brick, thermal resistance RT is given as the thickness of brick, which is 120 millimeters or 0.12 meters, working with SI units. The thermal conductivity of brick is given as 0.5. This is 0.5. And the particular area that we're dealing with is 5 meters squared. And so we have 0.12 divided by 0.5 times 5. So 0.12 divided by 2.5. That's approximately 0.048. And this is units again are Kelvin per watt. For the polystyrene, the thermal resistance RT, its thickness is 60 millimeters. We'll convert that to meters as well. So that's 0.06 meters. Its thermal conductivity is 0.006. And the area, of course, is the same. And so that gives us 2. So this has a thermal resistance rather of 2 Kelvin per watt. Again, it is a composite thermal conductor, and basically we'll treat it as conductors in series, and because they are conductors in series, we'll basically add the thermal resistances, and so therefore the total thermal resistance is equal to the thermal resistance of this layer of brick plus the thermal resistance of this layer of polystyrene plus the thermal resistance of this layer of brick. But because the 2 layers of brick are identical in terms of their dimensions, we'll just multiply the thermal resistance of one by 2 and add it to the thermal resistance of the polystyrene. So this is 2 times 0.048 plus 2, which gives us 2.096 Kelvin per watt. So that is the total thermal resistance of this composite brick wall. Having done that, we can now calculate the rate of heat flow through this wall using the formula Q over T is equal to the change in temperature delta T divided by the total thermal resistance RT. So we know the inner and the outer temperature as 18 and 14 degrees respectively. And of course, with this method, we do not need to know the temperature of the inner interfaces, right? We just need to know the inner and the outer temperature, or at least the change in temperature, delta T, or the temperature difference between the 2 layers, delta T. And so this basically gives us now 18 minus 4 is 14 divided by 2.096. And so this now gives us 14 divided by 2.096. Which is approximately 6.7 watts. Now, if we were to compare these two values, what we will now see is that basically, when the wall was simply 2 layers of brick, the rate at which heat was conducted through the wall was given as 146 watts. Now, however, by simply placing a layer of polystyrene of thickness 60 millimeters and of course thermal conductivity 0.006 between the 2 layers of brick, what has happened is that the rate of heat flow has significantly reduced, right? So therefore, this is essentially the purpose of insulating materials like polystyrene, to significantly reduce the rate of heat conduction through these type of materials. So that was question 3 from our worksheet on thermal conduction.